Now that we've talked about all the scenarios for horizontal circular motion, let's do a few examples with vertical circular motion. So if you have vertical circular motion, that means the rope or the circle is going to be spinning in a direction that's perpendicular with the surface. So an object moves in a vertical circle at the end of a rope. As the object moves, explains what happens to the speed of the object. The speed of the object in vertical circular motion is going to remain constant. This is just like before. As you come around, your velocity is still going to be tangent to the circle. Even though now we are vertical instead of horizontal, we're still tangent to the circle. All right, so the next thing wants to say, or wants us to tell, what is the force of gravity acting on the object? The force of gravity is also going to remain constant. But it is not necessarily going to be tangent with the circle. It always acts down. That makes sense. Gravity always acts down towards the ground, no matter where you are in your path. The last thing we want to know is what is the tension of the rope at the top of the circle and at the bottom of the circle. So we want to use a free body diagram to explain. So centripetal force, just like we had in horizontal, it's going to always act towards the center of the circle. All right, so if we are at the top of our circle, we are going to have our object that's going to be moving around the same way we had on the previous circle. You're going to have your tension force acting towards the middle of the circle. If the circle is like this and we're now at the top, it's pulling towards the center. You're also going to have your force due to gravity pulling down. That's always the case. You're going to have two forces acting on your centripetal force. But now when you're at the bottom of the circle, so if our circle is like this, you're still going to have that force due to gravity acting down. It always acts down. But our tension force is going to want to pull towards the center of the circle. So now they're acting opposed to each other. In this case, your tension force is actually going to be larger. We know it's going to want to keep coming straight back up. So our centripetal force, our net force at the top, would be acting down. And when we're at the bottom, our centripetal force is going to be acting up. Our net force is going to be greater up. At the bottom, it's going to be greater down at the top. So let's solve a problem for vertical circular motion. We have a student with a weight of 655 newtons. He is riding a roller coaster. The same student has an apparent weight of 1.96 times 10 to the 3 newtons at the bottom of the dip that has a radius of 18 meters. So this student is going through a loop-de-loop on the roller coaster. We want to first find what is the mass of the student. Before I get to that question, I'm still going to write out everything that we're given, all of our information. So our force due to gravity, remember, is the weight. This student's weight is 655 newtons down. Gravity always acts down. his normal force, or his apparent weight, at the bottom of the roller coaster is going to be equal to 1.96 times 10 to the 3 newtons. Remember, the normal force always opposes or always acts perpendicular to the surface. So it is going to be acting up since the surface is down or below. The other piece of information that we're given is that this circle or this loop-de-loop has a radius of 18.0 meters. So getting back to the question, let's figure out what the mass of the student is. This is similar to many problems we've done before. We know that the force due to gravity, or the weight, is equal to the mass times the acceleration due to gravity. When we rearrange, mass is equal to the force due to gravity divided by the acceleration due to gravity. We found in the question that the force due to gravity is 655 newtons, and the acceleration due to gravity is 9.81 meters per second squared. Even if this roller coaster is not on the surface of the Earth, it is going to be close enough that we can still consider it 9.81 meters per second squared. So we are going to have a mass of 66.77 kilograms. The next part of the question wants us to determine what is the centripetal force acting on the student. So remember, the centripetal force is the net force. It's all of the forces added together acting on a person or an object in a circular motion. So in this case, we are going to have the normal force, or the apparent weight, plus the force due to gravity. If I draw that out in a free body diagram, the force due to gravity is always going to be acting down. The normal force in this case is going to be acting up. The reason I'm taking a normal force that is acting up is because we are at the bottom of the roller coaster. That's the information we're given when it's at the bottom of the roller coaster. So it's going to be acting against the surface. It's going to be acting up. As we always do, I'm going to make up positive and down negative. Or we always need to give directional justification. In this case, I'm going to give positive up and down negative. So now we know the normal force, we know the force due to gravity, so we can plug in and solve. The normal force is 1.96 times 10 to the 3 newtons, plus the force due to gravity is in the negative direction. It's negative 655 newtons. So our centripetal force is 1,305 newtons, and it's positive, so the centripetal force is going to act up. The last part we are supposed to solve in this question is what is the speed of the student? Remember, we have this formula for centripetal force. Centripetal force is equal to mv squared over r. So we found out what the centripetal force was. We know from part A what the mass is. And in the question we were given what the radius is. So we can rearrange and solve for V. When we rearrange, speed is equal to the square root of centripetal force times the radius divided by the mass. When we plug in, we have 1,305 newtons times 18 meters divided by the mass, 66.77 kilograms, and we're going to want to take the square root. This gives us a speed of 18.8 meters per second.